Hello everyone. My name is Elodie Ngoie. I'm a student in Master's Computer Science from the University of Pretoria. I'm here to present to you our research on detecting cryptojacking in Bitcoin transactions using agnostic explanations. This research was conducted in collaboration with myself, Dr. Mike, and Dr. Tokmak. Cryptojacking as an unauthorized cryptocurrency mining has become a significant cybersecurity threat. It affects individuals, organizations by misusing computational resources. Today, I will walk you through our approach to detecting these attacks efficiently. Allow me to share my screen. Beg your pardon because I'm using two monitors, so you please bear with me. Share my screen. To start with, what exactly is cryptojacking? Cryptojacking is an unauthorized use of someone else's computer or device to mine cryptocurrency. This unauthorized activity leads to decreased system performance, increased operational costs. In some cases, it even goes to hardware damage. With cryptojacking growing in so much sophistication, traditional detection methods like signature-based model struggle to keep up, and especially when it comes to emerging threats. Next, our research aims to develop a semi-supervised machine learning approach, combining two powerful techniques such as autoencoder for feature extractions and random forest for classification. A significant challenge in this area is early detection. Traditional methods struggle or often fail to identify these attacks promptly. Furthermore, making this machine learning model interpretable is crucial, which is why we've included explainable artificial intelligence or XAI into our approach. Next. Our method is a hybrid model using autoencoders for feature extraction, as I said earlier, and random forest for classification. To that, we add lim, which is the XAI at this point. It is a local interpretable model-agnostic explanation technique to enhance interpretability. This combination allows us to detect cryptojacking effectively and provide insight into the model predictions. This is a representation of what the proposed model is. It is a three-layered model. On the first layer is the data that we're going to provide to the model. It's going to undergo feature engineering. Once that's done, we have on the second layer where we have the autoencoder and the machine learning model that we've chosen, in this case, the random forest. Once the model is built, the features are selected, we have tested the model, we can now, with the predictions, feed them into the lim and Lim is going to explain to us which feature have contributed mostly to the result that we've gotten. And this is into our third layer, and we can then visualize the results that Lim has given to us, which is human understandable. For analysis, we have used two datasets, namely UGRansome and the Bitcoin datasets. UGRansome contains over 200,000 data points focused on zero-day ransomware attacks like WannaCry, cryptojacking, etc. And Bitcoin is a bit larger than the former. It's about 2 million data point, real world data point, about Bitcoin transaction records. Both datasets provide a robust foundation for training and testing our model. Moving on to the next is our feature engineering phase and data processing. In this phase, we cleaned and processed the data, removing irrelevant attributes and encoding the categorical variable, because most of the algorithms, they take mostly integers. This refinement helped us to reduce the UGRansome dataset to approximately 149,000 samples, and the BitcoinHeist dataset to about 80,000 samples. This is to streamline our data for improved performance and accuracy. Moving on to the next, this is a figure that represents the autoencoder based, or I would say the feature extraction. What is the process of it? This is just a visual representation. So we have our data, we feed it as the input, and there is a series of autoencoders that will select or feature extract whatever is important in our data set, and then reconstruct it and minimize errors. Moving on to the next is how we employed the autoencoder to extract features. So it's more of compressing data into lower dimensional space, and then we reconstruct it with very minimal error, as I said previously. This now will be followed with the random forest, which would now classify these transactions as legitimate, as cryptojacking or not. Lastly, with the model, Lim provides the transparency by generating explanations for individual predictions, helping us now to understand the influence of the different features that we have in the dataset on our result. Next will be the mathematical representation of Lim. It has 3 steps. First step is to generate the perturbed samples. We have the model prediction, which has its own formula, and then the weighing sample and the linear model fitting. Moving on to the experimental setup. Our experimental setup split each dataset into training and testing sets using a 80-20 ratio, followed by 4-fold cross-validation. This allowed us to evaluate our model thoroughly on metrics such as accuracy, F1 score, recall, and so on, and precision, if I must be precise. In terms of the result, before I move on to the result, we have a visual representation of our experimental setup. So as stated earlier, our dataset consisted of UGRansome and BitcoinHeist, which we reduced dimension to the values that are shown on the figure, and we had some feature engineering happening here. Sorry for that. And after feature engineering, we fed that clean data into a series of autoencoders. Sorry again, I'm on the second screen. To now extract the feature that the most relevant or important features that we'll use, and fed that into our random forest, which has 100 trees. And after that, we tested. From the test, we could feed the predictions into LIM, then again explain the transactions. Moving on to the next. Our result. The result shows that random forest achieved up to 99% accuracy in predicting cryptojacking. This outperforms the autoencoder, which encountered more challenges with false negatives and positives. This high performance of the random forest indicates the robustness and accuracy in identifying cryptojacking attacks. Moving on to the next, so I think we have just few slides to go about. So this is just a table that tells what I just stated previously regarding the autoencoder, the autoencoder being outperformed by the random forest. As you can see there, random forest has achieved about 99% accuracy. When it comes to model interpretability with LIM allowed us mostly to delve into or to delve deeper into feature contribution. So which feature contributed to the predictions that we have. For instance, here I would say BTC income contributed about 24%, 24% to the predictions of illegitimate transaction. Additionally, we have seed addresses and network protocols were significant in distinguishing cryptojacking transaction. Visualizing this insight helps make our model more understandable and trustworthy. Moving on to the next, I think that would be the slide before the last one. I want to now tell the difference between our model and what is in the literature. So our hybrid model not only outperform existing methods in accuracy and precision, but also enhance model transparency through LIM. This transparency is essential for trust, especially in blockchain environment where understanding the feature significance is vital for risk mitigation, if I might say so. All in all, I would say The hybrid model using random forest and LEM proved to be effective in cryptojacking detection with high accuracy and interpretability mostly. And for future work, I would like to focus on exploring larger data set. Why not other techniques of explainable artificial intelligence such as sharp